Hello, class. So on this video, we'll continue on chapter 4. In the previous videos, or in the previous video, we talked about the method of undetermined coefficients. Basically, when you had an ODE equal to a function g of x, which was a combination of exponentials, cosine, sine, or polynomials. Right? In that case, you can still use the method of undetermined coefficients, and it works exactly the same as in the second order case. Right? How do you find your particular solution? You include terms that come from all possible terms that you get from all possible derivatives of your g of x. Right? So it works exactly the same as in the second order case. So really the only new thing is how to find the complementary solution, which we did in the previous example. Then we talked about the method of variation of parameters, right? And basically it was the same idea, right? You assume that your y sub p has this form, and we have u sub u1 times y1 plus u2 times y2 all the way up to un times y sub n, right? Where the y sub i's come from the complementary solution. Those are your n linearly independent solutions. And the u sub i's are not constants, but functions of x that are to be determined. So when you plug it into the ODE, you have to make these extra assumptions, right? That all of these expressions are equal to 0. And if you do those, then you end up with this simplified version of the ODE after you've plugged everything in. So then this becomes a system of linear equations where the undetermineds, or the variables that we have to find, are the u sub I primes, right? So u1 prime, u2 prime, all the way up to un prime. You can solve that using Cramer's rule. So you get this formula for each, or for u sub k prime, right? For the derivative of the ku function. And then I define what each of these are. W is just the Wronskian of the end linearly independent solutions, right? That came from the complementary solution. And W sub k is almost the same Wronskian, but you replace the kth row, right? Remember the kth column, the kth column is usually, the kth function, then its derivative, then second derivative, etc. Replace that column with a column of all zeros and g of x at the end. And then u prime k is that ratio, so you find u sub k by integrating both sides. So let's see an example. So solve the ODE, y triple prime plus y prime equals tangent of x. So for the method of variation of parameters, notice we can't use undetermined coefficients because tangent of x is not either sine, cosine, a polynomial, or an exponential. So if you take derivatives of tangent of x, you're going to end up with a really messy, each time you get derivatives, you're going to get new and newer terms. You're going to end up with infinitely many terms. So your particular solution, you can't include all of those terms and then try to determine each of those undetermined coefficients, because there's going to be infinitely many of them, or too many of them. So undetermined coefficients doesn't work. We have to use variation of parameters. This is a case in which we can find the complementary solution. Remember that for variation of parameters, we assume that we're given, or that we can find the complementary solution. So that's the first thing. Now, I believe that the complementary solution, okay, it's not the same as in this example. So let's go ahead and find it. Okay. So characteristic polynomial is going to be r cubed plus r, set it equal to 0. Okay. Factor out an r. Okay, so you get the roots, r equals 0, r equals I, and r equals minus I. So what are your three linearly independent solutions? Well, in this case, all of the roots have multiplicity 1. They're all distinct. Okay? So the solutions are just the exponentials with the root times x. Okay? So e to the 0 times x, which is 1. Here, remember that when we have complex roots with imaginary parts, they always come in pairs. Right? So that's something I mentioned in the previous video. And here you see that that's the case, right? We have I and minus I. So think of writing, so the roots in this case for the complex ones are r equals plus or minus I. So remember, all you have to do is determine what alpha and beta are. So alpha in this case is 0, beta is 1, right? And then remember that then the solutions have to form, let me use the same color as before. The solutions have to form exponential times alpha x times cosine of beta x, that would be one of them. Beta is 1, alpha is 0. And then the other one is the same, but you change the cosine for a sine. So to simplify these, we get cosine, because e to the 0 is 1. Here we get sine. So the complementary solution is C1 times 1 is just 1, plus C2 cosine x, plus C3 sine x. And these, again, this solution works for all real numbers. This is for I, negative infinity to infinity. Now, for variation of parameters, right, we already have the equations, right? So we're gonna guess a solution of the form, right? Because since we have the complementary solution, all we need to find the general solution to the non-homogeneous case is just find a particular solution. Right? So that's what we've been saying all this time. Okay. So in this case, we're gonna assume that we have a guess or a form for y sub p. Right? So it's third order. It's going to have three terms. So we're going to have u1, y1, plus u2, y2, plus u3, y3, right? Where the y sub i's, y1, y2, y3 are as above, and we have to determine u1, u2, and u3. Now, we have the equation to determine those, right? Because we have an equation for u prime. However, first let's check the assumptions. Right? So we have a complementary solution, right, that works for all real numbers, but we also have to check that the coefficient functions and g of x are continuous on an interval shared. That's a common interval with a complementary solution interval. So what are the p sub i's and g of x in this case? So first, if there's something multiplying the higher order derivative, you have to divide by that. Right? That's the first thing. Remember, that's how I give you the ODE in this case. And same in the second order case. For variation of parameters, you have to first divide by anything that's multiplying the highest order derivative. In this case, it's 1, right? So we don't have to divide by 1 because it's already 1 itself. So we're good. Okay? So what are the coefficient functions? Well, we have 1 for this coefficient. And then we have g of x being tangent of x. So we have, so p1, the coefficient function of the first derivative, is just a constant. And then g of x is tangent. Right? So we need these functions to be continuous on an interval shared by the interval of the complementary solution. So let's just pick the largest interval that works. P1 of x is 1. 1 is continuous everywhere. Okay. However, tangent is not. Right? So if you remember, tangent has infinitely many vertical asymptotes, right? Because tangent is sine over cosine. So whenever cosine equals 0, we have asymptotes, vertical asymptotes. Right? So this function is not continuous everywhere. So what we're just going to do is just pick an interval in which they are continuous. If an interval works better later, we can change it. But for now, we're going to choose let's call it I2, I guess. Negative pi over 2 to pi over 2. So cosine is 0 at negative pi over 2 and pi over 2, and multiples of that. Right? So we're just going to focus on this interval. So everything is continuous now on this interval. So we use I equal to negative pi over 2 to pi over 2. Now on this interval, all the coefficient functions are continuous, right? G of x is continuous, and it's an interval in which we have a complementary solution, because all real numbers work for the complementary solution. Now what we're going to do is find each of the u sub I primes. Right? Okay. So what's the formula? So let's say we want to find u1 prime. So by definition, this is the Wronskian w sub 1 over w. Now, what are these Wronskians? So w was just the Wronskian of, so let's do the work, and then we're going to put it in mathematically. Right? So actually solve the determinant. So w was the Wronskian of y1, y2, and y3, which are 1 cosine and sine. So y1, y2, y3, which are 1 cosine x and sine x, right? So this is going to be, by definition, right, just take each function and that becomes a column, right? So start with function y1. That gives you one column. Function y2 gives you another column. Function y3 gives you another column. Now, how many derivatives do you have to take? Well, the way I remember this is, so I first write the columns, right? So I'm going to have as many columns as I have functions, linearly independent functions. Then we want this to be a square matrix, meaning that we have as many columns as rows, or as many rows as columns, right? So since we have 3 columns, we need 3 rows. The first row is already this. We need 2 more rows, right? So we're going to have 1 row corresponding to the first derivative, another row corresponding to the second derivative. Okay. So that's how I remember it. You want to have a square matrix with as many columns as rows. So just take as many derivatives as you need until you have as many rows as columns. Okay. So let's start. Derivative of 1 is 0. Derivative of 0 is 0. Derivative of cosine is negative sine. Derivative of negative sine is negative cosine. Derivative of sine is cosine. Derivative of cosine is negative sine. So this is W. And again, this is a 3 by 3 matrix. We don't have a formula for the determinant. So we're just going to use Mathematica. Now, before I do that, let me write out what W1 is here, and then we're going to do all the work for the other ones in Mathematica. So what would W1 be? By definition, W1 is the exact same Wronskian as W, but you remove the ith column, in this case W1, or the kth column. So W1, we're going to remove the first column and replace it by what? Replace it by a column of all zeros with g of x at the end. Okay. So let's go ahead here. Right, so it's going to be the exact same Wronskian. We just replace one of the columns. In this case, we replace column 1 by what? Column of all zeros with g of x at the end. And everything else stays the same. The second column and third column stay exactly the same. So once we know what these determinants are, or these Wronskians, then we can write that U1 prime is this ratio, whatever these things are. And then we do the same for each of the other ones. So let's write out what W2 and W3 are as well, right, before I do this. Because so the denominator always stays the same in the formula. Oh shoot, I wrote this formula wrong. Yeah, sorry. So I wrote it correct above, but I wrote it wrong here. Should be like that. So the W's of K is in the numerator. Yeah, so I'm sorry about that. Yeah, so that's something that someone could have pointed out in class if we were face to face. But anyways, it's correct above. Right? So if you notice, the denominator never changes. What changes is the numerator, right? Is W sub K. So let's find the other ones. We found W1. W2 is going to be, again, the same Wronskian as W, but you replace now the second column. So the first column is the same. Second column, you replace it with a column of all zeros and g of x at the end. Third column stays the same. And then W3. First column stays the same. Second column stays the same compared to the first Wronskian, to the original Wronskian. But since it's W sub 3, you replace the third column with a column of all zeros and g of x at the end. So once we've found all of these determinants, we can find each u sub I prime, because u I prime is W sub I over W. So we'll go ahead and do this in Mathematica in the next video. But this setup, right, if you want to do some work, in your paper like this, which I'm going to require you to do, you can do this setup like this, and then I'll just tell you go to Mathematica and find what those determinants are in Mathematica. So we're going to do that in the next video.